Welcome everyone watching on YouTube. So this is our 52nd live stream geometry. So we've done a full year of them. And today I'm going to choose two problems that were suggested to me by different viewers and participants on my channel. And the rest of them I'm going to take from the USA TSTST. So that means the USA has a selection test for the IMO. And then there's another selection test for who gets to take that test. So I'm going to do the problems from that competition today. So if you would like to join me in any future sessions, feel free to email me at mgreenv801@gmail.com. And with that, I will start sharing my screen. Hold on just 1 second. So here's the first problem. So this was suggested to me. It's from the Serbia Junior Balkan Math Olympiad team selection test. Looks like a simple problem statement. So we have a triangle ABC with orthocenter H and circumcenter O. So I will use the algebra tool in just a minute, but for now I'm just going to draw the circumcenter and orthocenter. So that's the circumcenter. And then for the orthocenter, I'm going to use this. All right. And then we want to draw P and Q on AB and AC, so that APHQ is a parallelogram. So I'm just going to draw parallel lines through point H to AC and AB. And so these points will be P and Q, those two intersection points. So P is on AB and Q is on AC. And I'm going to hide the lines, so you just see the line segments. And it says we want to show that PB times PQ over QA times QO is 2. So I haven't done too many problems that have like an algebraic expression like this, but it's a pretty simple algebraic expression. So all right, so we have to use the fact that H is the orthocenter somehow. Maybe it's worth drawing AH and letting it meet the circumcircle. So we know that HD equals DE. All right, so PB times PQ. So I guess by symmetry, oh, this is not a symmetric expression, because so we know QA is equal to PH. So we could say this is PB times PH, or PB over PH, and then PQ over QO. That's interesting. So maybe we could find QO by using power of a point. So QA times QC is QO squared minus R squared. I don't know if that's the best way to do it. I see that just joined. Thanks for joining, Dat. So this is the first problem. It's a really simple diagram. So you just have a triangle ABC, H is the orthocenter, and then you draw this parallelogram APHQ. And we just want to show that this is true. PB times PQ over QA times QO is equal to 2. I highly doubt PB equals QO. Let's see. It seems very, yeah, no, PB isn't equal to QO, but.
Sorry, Michael.
Yes.
I have an idea. We can see that a triangle BPH is congruent to triangle HQC.
PBH and HQC?
Yes.
I think you mean they're similar, right?
Yes, yes. In Vietnam, we use word congruent.
Interesting. So, okay, so those two triangles, we can get a ratio. So you kind of, is that kind of just an angle chase?
Yes, just using angle chase.
Yeah, oh yeah, it's really because each of these are 90 minus angle A, and these angles are equal to angle A. In fact, these are both right triangles, right? Yeah.
Yeah, and next we will call the midpoint of PQ up. And we need to prove that triangle FQO is similar to triangle HQC.
FPO and HPC, or?
Yes, FQO is similar to triangle HQC.
HPO and FPO? That doesn't look. APO.
FQO.
APO?
FQO.
Okay.
Yes, and that will finish the problem.
FPO and APC. So basically we want to show a spiral similarity takes APC to FPO. Can you type those two triangles in the chat?
No, it is FQO.
Oh, FQO.
And HQC, yeah.
Okay, I'm sorry about that. That's my bad. I just have trouble hearing a little bit. Okay. So we want to show like a spiral similarity takes one to the other. So that's the same as saying that QFH is similar to QOC. And so one of those angles we could show is the same by an angle chase. And then if we can show FH over QH, so it's easy to show by an angle chase that angle FHQ equals angle OCQ. And then I think we could also probably show that FH over QH is OC over CQ. Let's see. Because just trying to think of the best way to do that. Yeah, is there a way to show that FH over QH is OC over CQ?
Okay, Michael.
Mm-hmm.
Okay, so we need to prove a triangle OFQ is similar to CHQ, which means that we need to prove FQH is similar to OQC, right?
Yes.
Yeah, and we have angle OCQ is equal to angle BCH, and BCH is equal to BAH, and BAH is equal to QHF.
Yes.
Yes, so we need HF over HQ is equal to CO over CQ.
Yes.
And which means that we need, if you call M is the midpoint of BC, if you call the midpoint of BC.
Okay.
Yeah.
1 sec, I'll call it M. Sorry. Point. So if M is the midpoint of BC.
Yeah, so OM is equal to FH, right?
Yes.
Yeah, so FH over OC. We need so FH over OC is OM over OC.
Yes.
And HQ over HC. QH over QC. Yeah, and two triangles CHQ is similar to CMO.
Oh, CHQ is similar to CMO, so that solves it. Nice. I missed that step where I use FH equal to OM. It's a nice solution. So I see a couple other people just hopped on, so thanks for joining. So I'm going to start writing it up. Okay, so all right. Let M be the midpoint of BC. Okay, so first we have so OM is equal to FH, well, which is well known. So that's well known. So I'll just start out up here, and F be the midpoint of AH. So basically triangle OMC is similar to QHC. So I'm gonna write this out. So we have angle HCA 90 minus angle A, which is 90 minus angle HQC. So angle QHC equals 90. So from there we have triangle OMC is similar to triangle QHC. And so we have FH over QH is OM over QH. QH, and that is the same as OC over QC. And then we also have angle FQH is equal to angle, or I'm sorry, angle FHQ is OCQ because, so I'm just going to write it out quickly. So angle OCQ is angle HCB I'll just say angle OCQ is 90 minus angle A, which is equal to angle PAH, which is angle FHQ. So that means that triangle FHQ is similar to QOC. So that, which means that FOQ actually is this similarity enough? So since FHQ is similar to QOC, sorry, or OQC. And then are the ratios enough? So that means that QO over FQ. So, oh yeah, okay. So QO over FQ equals QC over QH. Oops, sorry. Or sorry, OC. I'll say OC over FH. And that means that QO over QO over PQ over 2 is equal to OC is the same as, yeah, where do we use OC up here? Did I do this right? So OC is the radius, of course, but oh, we need that. We want that QHC and PHB are similar. We need to use that, right? Yeah.
Yeah.
Yeah. So oh. So basically, this means that QFO is similar to QHC. Triangle PHB. So that's using a spiral similarity. I see someone just wrote something in the chat. Oops, sorry. Hold on just a second. So is OM equal to FH? Yeah, OM is equal to FH because it's well known that, so yeah, I mentioned that here, but it's well known that OM is half of AH. Yeah. So yeah, I've used that a lot before my channels, but yeah, you could probably prove that using the Euler line. So so then once we have all this, that means PB over let's see, PB over PB over QO is equal to PH, yeah, PB over PO. PB over QO is PH over QF. hold on just a sec. So that's pH over QF. And that means that PB over QO is, we could just leave that as QO, but pH is QA. And QF is PQ over 2. And then that implies what we want to show. All right. Thanks everyone for your help on this. This is a fun one. Hey, what just happened here? All right, I see we have Anmol joining. So this should be C dot. Anmol, thanks for joining. Remember the parallel lines. Oh, are you, were you just talking to Bench? I'm not sure.
Yeah.
All right. So I'm going to move on to the next problem. So this is from the TST. So not the team selection test, but the selection test for the team selection test. So we have a triangle ABC, orthocenter and circumcircle. And then we have a line through the orthocenter. So whenever I see lines through the orthocenter, for some reason I think Pascal's theorem. I don't know if it'll be useful, but maybe it will. So it's any line through. So yeah, I'm gonna need to draw a line. But I'm gonna cheat here. So I want E and F. So E, this will be F. Then I'll delete point D. And then we draw the circumcenter of AEF. We let it be K. So K is the center of D. And then AK meets the bigger circle again at point D. Sorry for moving it around. Whoops. Sorry about that. I want something like that. It almost looks like AEF is isosceles. So I'm going to fix that in just a second. So we want to show HK and the line through D perpendicular to BC meet on the circumcircle. That's interesting. Whoops. Meant to click this one. So yeah, this is a very like general fact. I'm surprised I haven't seen this before. So I go close this, hide some stuff. So let me draw this point right here, point G. So it's the same as saying H, K, and G are collinear. All right. Move this up, maybe make this like a little bit smaller just so it's easier to see. I see someone just wrote something in the chat. Hold on just one second. We'll get there. There we go. I like that picture. So what if we show DG is perpendicular to BC? We could do that. We could let HK meet the circle at G. Either way works, I guess. So yeah, maybe we could try to use Pascal's theorem. So I want to use that this is the orthocenter, right? So if I let it meet the circle at 2 points, so J and L, then I think JE and B collinear? It looks like it. So yeah, it looks like we kind of have a Pascal's theorem configuration. I think we still have to prove it, but let's see. I don't know if that's obvious somehow by Pascal's theorem, but I think that's probably going to be useful. Yeah, and no, that is obvious by Pascal's theorem, because if we let DE meet the circle at J and we let DF meet the circle at L, then yeah, it would have to be true by Pascal's theorem. Okay, so we have that information.
Why?
Because let's say we let DE meet the circle at J and we let DF meet the circle at L, then, oh, that just means BL and CJ have to meet on this line, but it doesn't tell you they have to meet at point H. So yeah, you're right. We'd have to still prove something.
You draw the attitude from H, from A?
Yeah.
Yeah, okay.
I wonder if that's just an angle chase, though. So yeah, we know that BL and CJ should meet somewhere on that line EF. But yeah, it's not that obvious. But maybe it's not hard to show that it's point H, because if we can calculate angle DJC and show that it's the same as angle EJH. So I wonder if we have more cyclic quad. Let me try something here. So do these circles concur? Yeah, I think these three circles all like meet at a point. And so, yeah, I think that could probably be used to prove that these meet at point H. Let me make the figure better. So basically, if I draw this point right here, And I think we can prove that OJEH is cyclic, and similarly OLFH is cyclic. And then I think from there we can prove that CJ and BL intersect at H. I'm just guessing kind of, but yeah. I wonder if OH and D are collinear. No.
Okay. No, hold up. Don't reverse. Could you draw OH?
Yeah.
Yeah, and the attitude from A to EF.
Yes.
No, the whole line.
Oh, the whole line. Okay.
Yeah.
You wanted to see where it intersects?
No. And the altitude from A to EF. Yeah, they should concur on this circle.
Okay. Oops. Sorry. All right. Okay. So we have to show that H, K, and G are collinear. Let's see why they concur. Maybe we could show angle AEP equals angle, well, because angle AEP, we want to show it's angle QEP, but QEP no, we want to show AEP is EOP. I'm sorry, EAP is EOP, but EOP is EOH, which is EJH, which is DJC, which we can eventually show is the same as this angle. So I think that's how we show that. I don't know if it helps to draw these circles. Whoops. Let me see. So we have QHFL. So could we use the radical axis theorem here? Not sure. So JOEH, I'm just going to erase the circles for now, but let's see. Debye is joining. AK over KD equals what? AK over KD is HK over KG. Oh, Dubai, you've seen it before? Yeah. Don't solve it for us until, and if we get stuck, you can give us a hint. But yeah, that looks like so Manuel is suggesting yeah. Manuel is suggesting that maybe we show AK over KD as HK over KG. Or AH over DG. We could also do it that way. But yeah, Dubai, I think the very next problem is not a TST. So you might be able to solve that one, but the rest of them I chose TST or TSTST. But you could help us if we get stuck. Or if you find a different solution, like if we're trying a certain way and it's different than how you did it, you might be able to help us. Okay, so then maybe you can help us. Okay. So yeah, I think Vance was asking, how do we know OJEH is cyclic? Let's see, I'm actually not 100% sure. I just sort of saw that.
Sorry, Marco.
Yes.
I have seen this problem before, and let me show my solution. Okay. We need to sketch, to draw a lot of points and segment, and can you hide this? I think it isn't necessary.
Hide what?
You just hide everything which isn't related to the problem.
Okay. All right, so I'll hide OJL. This. Okay. Oh, hold on, I still need to hide this segments.
Okay, so we deduce that G is the intersection of the line through D perpendicular to BC and circumcircle ABC, and
Okay.
we need to prove that H, K, G are collinear. So first, we will let the circumcircle EBH intersect the circumcircle CFH.
EBH and FCH.
Yes.
Okay, and it looks like those meet on the big circle. So I guess you're going to prove that, right?
Yes. It's easy to.
Or what if, do you think we could let it meet the big circle and then we could prove that it lies on the other circle too? Or?
Yes. No. We will let T is the intersection of circumcircle BH, E, and CFH, and we will prove that T is on circumcircle ABC.
Okay.
Can you move some point? I think yes. T should lie under line BC.
Oh, okay. You want it to lie under line BC, like that?
Yes.
Kind of?
Yes. Yes.
Okay. Sorry. Maybe moving point E will make it better. Is that okay? Or you want me to move it more?
Yes.
Okay.
So we have angle BRC is equal to angle BRH plus angle CRH
Okay.
equal to angle AEF plus angle AFE is
And
equal to
that's 180 minus angle A. So then we know R lies on that circle.
yes,
Okay.
and you can draw the scope. And where point E, you high point E.
Oh, oops. There we go.
And we will prove that EKFR is concyclic.
EKFR.
Yes, just using angle chasing, and we will have angle ERF is equal to angle EBH plus angle FHC equals to 180 degree minus angle 2 times angle A, so it's equal to angle EKF.
Okay, that makes sense to me.
And we easily to have KHR is arcolinear.
Because how do we know that?
Just RH is angle bisector of ERF, right? And
Okay.
KE is equal to KF.
So RH is the angle bisector of ERF, is what you said, right?
Yes. And KE is equal to KF, so RHK must be collinear.
Okay. All right.
So last we need to prove RKG collinear, right?
Yeah.
So we have KE and KF tangent to KE tangent to circle BEH.
Okay. That's probably just an angle chase, right?
Yes, and so we have KE square is equal to KH plus KH times KR.
Mm-hmm.
So we have angle K. Let me see. Sorry, KA square equal to KE square equal to KH times KR.
Mm-hmm.
So angle KAH is equal to angle KRA.
Mm-hmm.
Angle to KDG.
I think I've got it. So
Yes.
KAH is the same as DAM, and then KAH is KRA, but basically angle GRA is the same as DAM because arcs GA and DM are the same. So that shows that they have to be collinear. That's a nice solution. I like it. All right, so I'm going to start writing it up. So let R be, so we could start out, let R be the intersection of those two circles. Whoops. So let R equal, I think it's BEH. It's BEH intersects CFH. And then we have angle BRC is BRH plus CRH. which is equal to angle AEF plus angle AFE, which is 180 minus angle A. And so that means that R lies on the circle ABC. And then once we have that, then we try to show KERF is cyclic. So so KE equals KF, and then so first we try to show, first we use an angle chase to show KERF is cyclic. So angle ERF equals angle ERH plus angle FRH, which is angle EBH plus FCH which is twice 90 minus angle A, which is angle EK, well, angle EKF is twice angle A. Wait a sec. So EBH, okay, so basically that's 180 minus 2 angle A, which is 180 minus angle EKF. So how do I space this out? Let me try that. Delete. See how that looks. There we go. So EKFR is cyclic. Okay, and then since angle ERH is angle FRH, so first I'll say this. I'll say since EK equals KF, then RK bisects angle ERF, and we also have angle ERH is angle EBH is 90 minus angle A, which is angle FCH, which is angle FRH. And so that means that K, R, and H are collinear. Then once we know that, it's not too much longer because we have arc GA is equal to arc DM. So let the perpendicular from G to BC meet gamma at G. And then that means arc DM is equal to arc AG. And so now it's just an angle chase, because then we have angle GRA is DAM which is KAH. Oh, we have to show the similar triangles. So this will be the last step. So KAH is KRA. And then that means that G, R, and K are collinear. And that means that HK, so I still have to show those similar triangles, so I'll do that in a second. Line through D parallel to BC meet on gamma. Let's see how this turned out. So it's saying, okay, I put an extra $sign there. Let's see how this looks. That looks pretty good. There we go. Okay, so I want to show that KAH is similar to AKR, and that's true because KA squared is KE squared. So we need to show KE and KF are tangent to the circumcircles of BEHR. So that's probably an angle chase. Yeah, so basically this whole calculation right here also shows that KE is tangent to BEH. So I'll just write that here. And then, okay, so since KE is tangent to BEH, then we can say, okay, so KA squared is equal to KE squared is equal to KH times KR. Means that KAH is similar to KRA. Cool. I like it. I like it. It's yeah, I think after the session, maybe I'll look for a proof that you did it like the way we thought about originally, but this looks like a cool way to do it. I like it. All right, so I will move on to the next problem. Okay, this is the one that most people had. All right. So now this problem looked kind of tricky. I don't know how many of you did the Discord Geometry Olympiad. Whoops, didn't mean to erase it. But who is telling me about this problem on Discord? It looks tricky though. So we have a triangle ABC with circumcenter O. And basically we see, we draw the three altitudes and we see where they meet the circle. And then we draw the lines through O. We see where those meet the sides. So if this is O, we draw AO, BO, and CO. So basically those are isogonal to the other three lines. And we see where they meet the sides. So AO meets it there, BO and CO. And then I'm going to rename these, but then we see where the altitudes meet the circle. So, okay, so this is A1, B1, and C1. And then this is A2, B2, C2. To C2. I'm going to make it look nicer. All right. So basically we want to draw the circumcircles. I'll draw the orthocenter H. But basically if we draw A1, A2, B, B1, B2, and C, C1, C2, they have two common points. That's what we want to prove. It's kind of a weird thing to prove, but makes sense? I'll be right back, guys. All right, thanks for waiting. Sorry about that. So yeah, is there anything, I wonder if H lies on the radical axis of these circles.
It does.
It does, okay. So there's something special about this line. So then maybe what we could do, we could let, well, if we let two of the circles intersect at 2 points and we show that that passes through H, I guess the same could be true with another two. That would also pass through H, but they wouldn't be the same line necessarily, which is what we have to show. But that might be a step forward at least. I wonder. Like maybe we should just draw two of the three circles. So like I could hide A1, A2 for now. So I could, if we just drew these two circles, could we show that it passes through H? And then it would be true for the other pairs, and then there would still be one more step, then we'd have to show it's the same line. So can we show, oh, does H have the same power with respect to those two circles? Yeah, right, because BH times HB1 is HC times HC1. So yeah, basically since H has the same power with respect to those circles, yeah, it's just the radical axis theorem, right? I don't even need, yeah, by the radical axis theorem, BH and E are collinear. And then we need to show that BE A1, A2 is cyclic. Or DE, like all 5 of those points lie in a circle, basically. So yeah, we could actually forget, we just need to really show it for one of them. So BA, A2, A1 is cyclic. See you, Dubai. Thanks for joining us. Yeah, even if you guys have to hop off early, it's fine. I still appreciate it. So okay, so we want to show DE A2 is, or DA A2 A1 is cyclic. What angles can we calculate? We know angle A1 A2. We can calculate that. What about angle A1B A2? That's kind of hard to calculate. Maybe we could use the power ratio lemma, right? Because I kind of like the power ratio lemma idea. So we want to show the ratio of the power of A with respect to these two circles. I mean, really, we need to show it for all 3 of these points, right? So what would the power of A with respect to this circle be? I mean, maybe we could extend BA to meet it.
Maybe we should try S squared to BC inversion.
Root BC, square root of BC
Yes.
inversion?
Yes.
Okay.
Because we have the isogonal lines and things like that. So it may be good.
Okay, so that would sort of swap B and C, right? But like, do you want to also reflect it over the
yes.
angle bisector? So B and C would be swapped. We also know, like, would A2 and A1 be swapped? I think because
Yeah, they would.
okay. So let's see, that's interesting. So A2 and A1 are swapped. So the circumcircle would stay the same, right?
It would go to a line.
Oh, we go to the line A2, A1.
Yeah, DA, A2, E, A1 would go to a line. A1, A2, yes.
Okay. So A1, A2 would go to a line, and then those two circles. I guess I'm not sure where the two circles would go to. Let's see. Oh. But yeah, it looks like it's a really good idea for, like, I like how it swaps A1 and A2. I just don't know what to do with B1 and B2. Let's see when it's E2. Could it swap them also? I don't think so. Yeah, if you can think of a way to do it, let me know. I like the idea. Okay, let's see. So we want to show, well, first of all, can we show D, A, E, and A1? So I think by power of a point, we could probably show D, A, E, A1 is cyclic, right? Because
Yeah, we can.
yeah, so we just need to show A2 lies on that circle. What we could do is we could draw that circle and we could let it intersect BC at a point. So maybe A2 prime. Oh, but we don't know it passes through O. That's the, oh, but it doesn't pass through O. So we could call this A2 prime. And then we want to show that A, O, and A2 prime are collinear. I don't know if it helps to draw this point. So angle, we know angle OAC, and we want to show that's equal to angle O A prime A2C. I'm sorry, A2 prime AC. Is there any other way to calculate A2 prime AC? Can we use similar triangles somehow? So what are the similar triangles? So what was it? So AHB is similar to AO. Get how this worked. Not AOC, right? Does AB times AO equal AH times AC? I don't think so. I don't think that's true. But I'm trying to thinking like root BC inversion. Maybe we could show A2AC is similar to some other triangle. Like if we draw this point, so basically we want to show A2 prime CA is similar to A1B. That would solve it. And so we know one of the angles is the same. Maybe we should let BC intersect this circle, the point. I don't know if there's something special about that point. Hold on a second, guys. Let's see. No, I don't think there's anything that special about them. Oh, maybe, let's see. Yeah, it doesn't look like it. I don't know if GA1 is tangent or that's just a coincidence. Oh, it kind of looks like that. Yeah, it looks a little like GA1 is tangent to the circle. Interesting. So maybe that will help. I'm going to try to use that fact. Let me make sure that that's actually true. It looks true. Yeah, because then we would have GA1A is GA2 prime A. And we want to show that is we want to show that's 180 minus angle C. No, we want to show that's angle C. So hold on a sec. That's weird. It's GA1A. Oh no, not 180 minus C, 180 minus this angle. Just C plus 90 minus B. So what if this was tangent? Then it would, yeah, then we would get the angle that we want. So yeah, basically, if we can show that this is tangent, it would solve the problem. Oh, G. Yeah, G right here. G is the intersection of the circle BAEA1 with BC. So I proved that BAEA1 is cyclic. So D and E are defined based on the circles B, B1, B2, and C, C1, C2. And we proved that DH and E are collinear, and we proved that DAEA1 is cyclic. So I take that circle and I let BC intersect that circle at point G. And if I can show that GA1 is tangent to the circumcircle of ABC, that would solve the problem. Let's see. B1. I wonder if well, so GA1 is equal to GH. So, I mean, basically, we just want to show that angle GHB. So yeah, we want to show GHB is 90 minus B. Is that right? Yeah, I think so. So, it's interesting. So is GHB tangent to AH? Yeah, that looks true. Is that obvious? I think that would also solve the problem. So if we could show either of two tangencies, that would solve it. Two different tangencies. If you could find one, it solves it, or if you could find the other, it would solve it. It's tricky though, because D and E are defined in like a strange way. So it's maybe not as easy as it might seem. We know GA equals GH. Does this circle, I don't think these three concur. Okay. No, that's just like an illusion. So I think so what would the center of that circle be? And I wonder if IA is tangent to that circle. No. Maybe we could use the power ratio lemma. I have a feeling that might be the best way to do this. So let's see, we have this circle right here. B1, B2, or no, C1. No, that's just a circle of ABC. We have this circle. So yeah, I'm trying to use the power ratio lemma. So we know A1 and A. So we know the ratio of the powers of A with respect to that and this. So these are the two circles, right? And A and A1 have the same ratio of powers with respect to them. So G, since G lies on the circle and A2 also lies on it, they have the same ratio of powers with respect to them. Maybe that would help. So let's see, I have this circle. I'd have to draw this point. And then I have this circle. You know what we could do? We could just define A2 normally and show it has the same ratio of the powers with respect to those circles. So I'm not exactly sure how we would calculate that. Right, so we're about halfway through. Do you guys want to try moving on to the next problem? See, we have another person that just joined. So, are you someone new or are you Dat Thung?
I'm Dat.
Okay, all right. So I think I'm going to move on to the next problem for now. We can come back to this one later. Looks interesting though. I think we might be close.
Michael. The problem is from 2021 GEO.
I think so. Yeah.
Okay.
All right. So yeah, it's the